Hey everyone, welcome. I am absolutely thrilled you're here today because this explainer covers something that is, quite literally, quietly powering choices all around us. We are taking a deep dive into the weighted sum model, or WSM for short. If you're at all fascinated by how we structure logic and arrive at optimal conclusions, you are going to absolutely love this. WSM is considered the earliest, the simplest, yet arguably the most foundational multi-criteria decision algorithm out there. It all starts with a universal problem. So think about it for a second. How do you mathematically guarantee you're making the absolute best decision when you've got multiple, completely competing priorities? Say you're choosing a new vendor for your business, or even just buying a house. You obviously care about cost, quality, location, and speed. But you can't just maximize one of those things without hurting another, right? We really need a way to synthesize these conflicting goals into a single, undeniable conclusion. And that is exactly the mathematical solution the weighted sum model provides. Okay, let's dive into this. Here is our roadmap for today. 1. The decision-making dilemma. 2. Anatomy of the matrix. 3. The WSM formula in action. 4. The apples and oranges flaw. 5. Testing WSM through sensitivity analysis. And finally, 6. Embracing uncertainty with fuzzy WSM. Section 1. The decision-making dilemma. Now, if every single option was both the cheapest and the absolute highest quality, well, decision-making wouldn't really be a science. It's the trade-offs that make it a dilemma, and that dilemma is exactly why we need the weighted sum model, widely known as the grandfather of all multi-criteria decision-making, or MCDM methods. It's kind of crazy, but despite all the incredibly advanced algorithms out there today, WSM is still incredibly relevant and widely used. Why? Because its underlying logic maps so perfectly to how the human brain naturally weighs pros and cons.
Section 2, Anatomy of the Matrix.
Let's break down the strict requirements for our inputs. We basically start with a decision matrix, which is just an M by N grid. Our alternatives, the actual choices we're deciding between, sit nicely in the rows. Our criteria, the things we're judging them on, form the columns. And finally, the secret sauce here, the decision weights. Each criterion must be assigned a weight of relative importance, and crucially, these weights are usually normalized so that they all add up to exactly 1, or 100%. And this brilliantly illustrates the concept. We've taken all that abstract theory and grounded it in a concrete numerical example directly from our source material. Notice the layout here. We have 3 alternatives, A1, A2, and A3, listed on the left. Across the top, we have 4 criteria. Now, look closely at those numbers in brackets, right next to the criteria. 0.2, 0.15, and so on. Those are normalized weights. So criterion 3 is clearly the most important here, carrying 40% of the total decision weight. Inside the grid itself are the actual performance scores for each alternative. Section 3, the WSM formula in action. All right, so now that our matrix is fully loaded and structured perfectly, it is time to move from the inputs to the engine itself. The math here relies on what is called the additive utility formula, and mechanically, it's just very elegant. First, you take the performance score of an alternative for a specific criterion, and you simply multiply it by that criterion's weight. So if we look back at alternative 2, for criterion 1, it scored a 10, and the weight was 0.2. 10 times 0.2 is 2. Step 2, you literally just repeat this for every criterion in the row, and you add all those numbers together. Step 3, do this for every row, compare your final sums, and rank them to find the highest value. Simple, right? And when we run that exact math on the matrix we just looked at, alternative A2 emerges as the clear winner with a total score of 22.00. For context, alternative A1 scored a 21.50, and A3 scored a 20.00. By simply multiplying the scores by their weights and summing them up, the math has objectively synthesized all of those conflicting columns into a single decisive ranking. Section 4. The apples and oranges flaw. But hold on a second. Before we go declaring WSM the absolute perfect tool for every single problem, we really have to discuss the fundamental limitation of this grandfather model. The key vulnerability lies in its core premise, the additive utility assumption. This brings us straight to the classic apples and oranges analogy. You see, the math of WSM works beautifully if all your criteria are measured in the exact same units, like if everything is evaluated on a unified 1 to 100 scale. But out in the real world, you might be comparing cost in dollars, distance in feet, and time in seconds.
You cannot mathematically add dollars to feet and then a logical sum without heavily normalizing the data first. If you try to do that, the model completely breaks down.
Because of this pretty major flaw, decision scientists had to evolve the model. We can see a great comparison of how that happened. While WSM relies on addition and struggles with mixed units, a sister model called the weighted product model, or WPM, was developed. WPM relies on multiplication. It raises each value to the power of its weight and multiplies them together. This creates what mathematicians call dimensionless analysis, which neatly eliminates the whole unit problem entirely. So if you're dealing with raw dollars and feet, WPM is for sure your go-to upgrade. Section 5. Testing WSM, Sensitivity Analysis. Okay, assuming our data is properly scaled, what actually happens when we really stress test the WSM engine? Like, how fragile is that winning score of 22.00 we calculated earlier? Now, what's really interesting about this visual from our source text is that it maps out the exact mathematical thresholds where a winner suddenly becomes a loser simply because a single criterion's weight shifted slightly. This is called rank reversal. Sensitivity analysis essentially asks, if I change the importance of cost by just 5%, does my number one choice suddenly drop to number two? Understanding these thresholds is absolutely crucial, because if your decision is highly sensitive to a tiny change in subjective weights, you might not have as solid a conclusion as you think.
Section 6. Embracing uncertainty. Fuzzy WSM.
So what do we do when our inputs just aren't perfectly precise? Because, let's be real, the real world is messy. Enter fuzzy WSM. Sometimes you don't have a hard factual number. Sometimes a weight isn't exactly 0.2, but rather, around 0.2. Fuzzy WSM allows us to input ranges instead of strict numbers. It does this by replacing single data points with what are called fuzzy triangular numbers. This means instead of one rigid number, you give the model a lower bound, a modal, or most likely bound, and an upper bound. The algorithm then runs the weighted sum across these ranges, giving you a much more robust and forgiving decision model that actually respects human uncertainty. Now, what is truly amazing about everything we've just covered today, from the standard matrix to these more complex calculations, is how computationally lightweight it all is. As our sources highlight, both WSM and WPM calculators can actually be built in pure JavaScript in less than 50 lines of code. No joke. This powerful math is incredibly accessible, meaning it's wonderfully easy to implement these decision engines into modern web tools and everyday dashboards. But as we wrap up, I want to leave you with a slightly provocative thought to ponder. We've seen how elegant and how strict the math of the weighted sum model really is. But if the mathematical engine is perfectly logical, how much should we honestly trust an algorithm whose entire foundation, meaning the weights of importance, are determined by subjective human opinions? The math itself won't fail you, but did you assign the right weights to begin with? It's a fascinating philosophical question sitting right at the heart of decision science. I really hope this explainer has given you a powerful new framework for tackling your own complex choices. Thanks so much for joining me, and keep questioning how we make decisions.